Okay, this is the second video on vectors, and now we're going to look at what's called a unit vector. And it should be pretty obvious at this point in all the math you guys have done. I'm sure you've heard references to units before. And if you think about it, when we do, say, prime numbers, you have prime numbers, composite numbers, and you have the number 1, which is called a unit. You talk about unit fractions. You talk about, say, a unit of measure, 1 foot, 1 inch. We talk about the unit circle, a circle of radius 1. Unit generally refers to 1, a base unit of measure. So when we talk about a unit vector, essentially a unit vector, or what we'll generally say is a unit vector in the same direction as a vector v. What we really mean is, given some vector, say we have the vector, we'll go with 2, 4. Say it's right there. So say I have that vector right there. I want to find a unit vector in the same direction as that vector, which means I want to find some vector that's going in the same direction that has a magnitude of 1. Clearly, we can do the math in a minute. This vector has a magnitude greater than 1. I want to find one that has a magnitude of 1. Logically, in the last video, we mentioned that you can do scalar multiplication, and you can take some vector, in this case v equal 2, 4, and you can multiply it by a scalar to make it bigger or smaller. So essentially what I'm looking for is some number that I can multiply this vector by, some scalar, that will shrink it down to a magnitude of 1. Or if this vector somehow had a magnitude less than 1, something to multiply it by to make the magnitude bigger, so it equals 1. And there's actually a trick to doing this. Well, find the magnitude of this one first, just so I know what I'm talking about. So let's see. If I do my triangle, this side is length 2, that's 4. 2 squared is 4, 4 squared is 16, 16 and 4 is 20. So this is root 20. Now I just want to shrink it down. And what I can actually do is, if the magnitude of the vector of this vector is root 20, divide by root 20. Because root 20 divided by root 20 is 1, which is the magnitude I want. So I'm going to take this vector v right here, and I'm going to do 1 over root 20 times v. Which is just, let's see, we distribute it in. That's 2 all over root 20, 4 all over root 20. I'm aware that's not in perfect standard form. For the purposes of this, I'm not going to simplify the radicals. I want to leave them like that on purpose. Because now we have this vector. It's clearly in the same direction. I just multiplied by a scalar, which makes it bigger or smaller. Now I just need to make sure that it actually has a magnitude of 1. So find the magnitude. Well, like we said last time, the magnitude is just the distance formula, which is really just this squared plus this squared square rooted. That's the x component, that's the y component. Square them both and add them and square root them. If I squared this out, 2 squared is 4. That marker's not working anymore. 2 squared is 4. All over root 20 squared is 20. Plus 4 squared is 16. All over root 20 squared is 20. I get 4 plus 16, 20 over 20, which is 1. And then the square root of 1 is obviously 1. Which means this vector right here has a magnitude of 1. And it's in the same direction. So that's my unit vector in the same direction as v. The actual formula as it's written in your book, to find this unit vector, you do 1 over the magnitude of v times v. Find the magnitude, Pythagorean theorem, and then multiply by the reciprocal, 1 over the magnitude. Don't get lost in the terminology and the notation and how it's written. The principle is pretty straightforward. Find your magnitude, and then divide everything by it, because you want to take the magnitude divided by the magnitude to get 1, which is the magnitude you want. So it actually makes sense in principle. So let's see. last video and this video, you can take a vector, you can write it in different forms, you can move your vectors around, you can add them, subtract them, multiply them by a scalar. Now you can find a unit vector. There's one other thing we want to go over for right now. That is writing a vector as a linear combination. And the idea is, well, we know when I have vectors, suppose I have some vector that looks like this right here. We'll just call this the point 5, 3. And that's my vector. We know from the previous video that I can write two vectors graphically, and I can combine those two vectors graphically to get a new vector. We used v and w before. So what I mean is, suppose I had this vector right here, the vector along the horizontal. This will go to the point 5, 0. Then I had this vector along the vertical. That will go to the point 0, 3. So if this is my v and this is my w right here, what happens when I get v plus w? Well, we do the nose to tail thing. If this is v, I take w and I add it to the tail of v. I get that. And then the resulting vector, going from the origin to where I finish, is v plus w. I mean, I know that's pretty obvious just from looking at it, but mathematically speaking and from problem solving perspective, it can actually be very useful to take a vector that is not horizontal or vertical, that's just anywhere in the plane, and to break it down into a horizontal vector and a vertical vector, so you're only dealing with one dimension. So now what we want to do, when we say writing a vector as a linear combination, essentially the way we write it in math is we say something like, we'll just use v again, v equals ai plus bj. Essentially, the I and the j are my dimensions. I is the x dimension, j is the y dimension, and those are unit vectors right there, which means these have a magnitude of 1. They're just the horizontal and the vertical. The a and the b are just the scalars from our scalar multiplication that we multiply by, and then we want to be able to get this resulting vector right here. So for the purposes of this one right here, well, if I want 5, 3, then my vector would be 5i plus 3j. Because that's 5 in the x direction, 3 in the j direction, and I end up right here, which is the vector 5, 3, the one I want. I'm assuming that at least looks a little straightforward. It's just a different way to write a vector that we are going to use for problem solving. So for the sake of argument, suppose, say we have this. I have a 100-pound force applied at a 45-degree angle to the horizontal. Find the force vector written as a linear combination. Okay, so essentially this sounds like a physics problem because it mentions force and all of that. So the way this works is, say that's my ceiling right here, and then I have a 100-pound force applied at a 45-degree angle. This will obviously be hanging down, so that's a 45-degree angle right there. And the force is 100 pounds, which means the magnitude here is 100 pounds. Obviously, if you're drawing this out, you can draw it out lots of ways. The best way to do it is to make this the origin right here. And now we're just dealing with that angle right there. Now we want to write a linear combination of this vector right here. Which means I need to find a horizontal component, this one right here, and the vertical component right here. And then write the combination so that when I add them, I'll get that one. Well, think about it. We have my wonderful, oh, let me get different colored markers. We have my wonderful triangle trigonometry, so I can draw this right here. There's my right angle. And now let's see, the length of this side and the length of this side is what I want. Well, if that's 45, I know this is 100. Then if that's 45, that's the adjacent side. So that would be cosine of 45 degrees equals adjacent, which is x, all over hypotenuse, which is 100. Multiply the 100 over, and we get x equals 100 cosine 45 degrees. Cosine 45 degrees is root 2 over 2. So x equals 100 times root 2 over 2, which is 100 over 2 is 50, so that's 50 times root 2. You can throw it into your calculator, it doesn't really matter. But there's my x. I can find my y, that's right here. Doing the same thing. If that's 45, this is the opposite. That's sine. So sine 45 degrees equals opposite y over hypotenuse 100. Just like we did over there, multiply the 100, y equals 100 sine of 45 degrees. That's root 2 over 2, so we're going to end up getting the same thing. Y equals 50 root 2. But now we found the magnitude of this vector and the magnitude of that vector, so now we can write my linear combination. F, because it's a force vector, we'll just call it F, equals the horizontal component, which is 50 root 2 I, plus the vertical component. But keep in mind here, the vertical component is actually downwards, which means this is actually negative. So it's minus 50 root 2 J. And there's my vector right there. 50 root 2 in the horizontal direction, negative 50 root 2 in the vertical direction. Your book actually gives a formula for this. I'll write it out again. If you understand the principle of drawing the vector and the triangles and all that, then you can solve it without necessarily using the formula. But the formula your book actually gives is to write a linear combination, then we'll just use V. V equals magnitude of V cosine theta I plus magnitude of V sine theta J. But that's exactly what we did here. To find the ith component, the x direction, we found the magnitude 100 times the cosine of theta, root 2 over 2 in our case. For the y value, we did the same thing. The magnitude 100 times the sine value, root 2 over 2. The one thing to keep in mind, if you're going to use that formula, the theta that you plug in is not that theta, it's the theta from the horizontal, which means that's the theta for this one, 315 degrees. Because then the cosine of 315 is positive, because it's in the fourth quadrant. The sine of 315 is negative, which is what will make that negative. Again, as long as you understand the picture, you'll just say, oh wait, it's going downwards, so this has to be negative, so it's a minus right there. If you're not convinced you'll remember that, just remember you can use this formula. Your angle comes from the horizontal, so you don't use the acute reference angle, you use the full angle from the horizontal. We're going to do more with this, but I'm going to leave this video right there as it's a lot of material.